the 1970s, many relay manufacturers introduced electronic relays, which simply emulated their electromechanical predecessors, and in many cases, the design still required costly periodic calibration. In the early 80s, the microprocessor-based relay, or digital relay, was introduced. Standard features such as multiple element support, low maintenance, built-in high-speed communication, waveform, event log, improved element performance, and built-in programmable logic controller functionality has enabled the digital relay to revolutionize the protection industry. Let's take a closer look at the operation of a modern microprocessor-based relay. Through the use of current and voltage transformers, the relay receives information about the power system. These quantities are converted into symmetrical components and passed on to the active protective elements within the relay. The protective element or elements within the relay initiates the appropriate action based on these quantities and the configuration settings within the relay. These elements may work independent or through the use of logic gates. The type and number of protective elements within a particular relay will depend upon the type of protection application the relay has been designed for. For example, a relay designed to protect a transformer will have some protective elements not found in a relay designed to protect a feeder, and vice versa. The American National Standards Institute, or ANSI, has assigned a device number for each protective element. A single line diagram showing the protective relay's connection to the power system, along with the supported ANSI device numbers, has become a popular form of summarizing the capabilities of a particular protective relay. Here's the single line diagram for the F60 universal relay. Here's the single line diagram for the F35 relay. A quick comparison of the two diagrams summarizes the differences between the two relays. The F60 has many more protective elements than the F35, but is designed to protect a single feeder. The F35, on the other hand, may not support all the protective elements that are supported by the F60, but can support up to 6 feeders. If the elements supported by the F35 were sufficient to protect a given group of feeders, the F35 would be a more economical solution than 6 separate F60s. Instrument transformers supply protective relays with current and voltage for measurement. This high current and voltage is first converted by the transformers to much lower quantities that can safely be injected into the relay for measurement. It is important to note that the proper selection of current and voltage transformers for protective relaying applications is the responsibility of the system engineer. CT's introduction. The function of a current transformer, or CT, is to take a current flowing through a wire or cable and step it down to a magnitude that a protective relay can measure. A primary characteristic of CTs is their conversion ratio. In this example, our conversion ratio is 100 to 5, meaning that if 100 amps are passed through the primary phase wire, the CT will scale this down to 5 amps and direct it to the relay via the secondary windings. The 5 amp measure is known as the secondary nominal current. If a fault were to occur on this phase that increases the primary current to 200 amps, then 10 amps would be passed to the relay through the secondary windings consistent with the ratio. CTs have two types of secondary ratings, 5 amps and 1 amp respectively. 5 amps is typically the North American standard, while 1 amp is used in Europe and Asia. Primary ratings are available in various different levels, for example 100, 150, 200, etc. Types of CTs. A common current transformer construction is one in which the power system phase wire is passed through the hole in the center of an annular core or ring, which is called a window. This forms the primary winding. A second insulated wire is then wound around the core and then brought to the relay for measurement. This is known as the secondary winding. A CT with this type of construction is typically referred to as a toroidal or donut style of CT. CT selection. Proper protection starts with the selection of current transformers. The following is a simple procedure that can be used to check whether or not there is the possibility of CT saturation. This procedure is as follows. The first step is to ensure that the primary rating of the current transformers is equal to or greater than the expected full load current. We can determine the primary rating of a CT by looking at its ratio. For a ratio of 100 to 5, a CT has a primary rating of 100, meaning that no more than 100 amps should be passed through the CT under normal operating conditions. The second step is to ensure that the CT can drive what is called the attached burden at the worst-case fault current levels without saturating. The burden refers to the total load resistance of the secondary circuit. The calculation for the burden is CT secondary resistance, which is the amount of resistance on the secondary windings on the CT, added to the connection wire resistance, which is supplied by the manufacturer, added to the relay's burden resistance, which is the resistance within the protection relay. As explained in the previous section, a CT becomes saturated when the voltage secondaries reach the knee point of the excitation curve. To determine whether the CT can drive the attached burden under worst-case fault conditions without saturating, we must determine what the CT's secondary voltage will be at the time of this fault. The CT secondary voltage at the time of fault is equal to the burden resistance times the maximum fault current divided by the CT conversion ratio. The resulting value is then plotted onto the CT excitation curve. If the value plotted on the curve is below the knee point, then the CT will not saturate under these worst-case fault conditions. If the value is equal to or greater than the knee point, then the CT will saturate. Now we will look at a practical example to help us further explain this calculation. Let's assume that we have a motor that draws a maximum full load current of 285 amps. The first step is to choose the appropriate CT. It is customary to select a CT that has a primary rating falling between 50 to 100% of our maximum full load current, in this case 285 amps. Possible CTs for this use would be 300 to 5, 400 to 5, and 500 to 5 CTs, because the primary rating falls between 50 to 100%. In this case, we would select the CT that would fall the closest to 100%. The reason for this is the higher the CT ratio is over the full load current, the less sensitive that CT will be. Since accuracy is always imperative, we will select a CT with a 300 to 5 amp conversion, where the primary rating is 300 and closest to the 100% primary rating. The next step is to ensure this CT doesn't saturate under worst-case fault conditions. If it does, a higher ratio CT, such as the 400 to 5 CT, may need to be chosen. The first step in determining whether a CT will saturate is calculating the maximum current that will appear on the primary of the CT under a worst-case fault condition. The maximum fault current at the load is determined by a fault study, and in this case was determined to be 6,000 amps. Next, we will calculate the secondary resistance, or burden, using the stats provided. The phase CT's secondary resistance, that is the resistance of the windings on the CT, is equal to 0.088 ohms. The length of each wire from the CT to the relay is 50 meters and has a rated resistance of 2.5 ohms per kilometer. The total burden is equal to the CT secondary resistance, which is 0.088, plus 2 times the lead length of 50 meters multiplied by the lead resistance of 2.5 ohms per kilometer, and then divided by 1,000 meters. This is then added to the relay burden of 0.008 ohms, resulting in a total burden of 0.346 ohms. Now the secondary voltage at the time of a worst-case fault can be calculated. First, the total burden resistance, 0.346 ohms, is multiplied by the maximum fault current, 6,000 amps. The result is then divided by the CT ratio, 300 to 5, concluding that the secondary voltage at the time of a worst-case fault is 34.6 volts. With the maximum secondary CT fault voltage calculated, the final step is to refer to the CT excitation curve. By plotting the 34.6 volts value on the excitation curve, we notice that it falls well below the knee point, indicating that it will not saturate under a worst-case fault condition. If the factors affecting the burden were ever to change, or a higher fault current is measured, these calculations must be repeated to ensure the CT does not saturate. Potential transformers. The next type of transformer we will cover is the potential transformer symbolized as PT, or sometimes known as voltage transformers symbolized as VT. Similar to current transformers, potential transformers scale down the voltage passed through them, as opposed to the previously mentioned current. The scaled-down voltage is then routed to a protective relay for measurement. Also as in current, a PT is classified with a conversion ratio indicating the amount the primary voltage is scaled down. For example, 60 to 1 scales the primary voltage down to 120 volts. There are two different types of potential transformers used today: the electromagnetic voltage transformer and the capacitive voltage transformer. Electromagnetic voltage transformers are usually used when accurate metering needs to be performed for lower voltage applications. Capacitive voltage transformers are commonly used in high voltage transmission line applications where the voltage is higher than 66 kilovolts. Electromagnetic voltage transformers have dense winding drops designed to accurately scale down the voltage and make sure the ratio is consistent for all variations in the input voltage. Due to the small amount of voltage drops per winding, the electromagnetic voltage transformers will increase in size as the rated primary voltage also increases. Likewise, the cost of electromagnetic voltage transformers tends to increase at a disproportionate rate to the primary voltage rating. Capacitive voltage transformers, or CVTs, are normally used on higher voltage applications. The CVT is basically a capacitance potential divider and consists of the following components: coupling capacitors, typically 10, compensating reactor, step-down transformer, and a ferro-resonance suppression circuit that is found just before the output terminals for connecting to a relay. The accuracy of a PT's operation is specified in the displayed label format. The first item in the label indicates the accuracy class of the PT. The three common accuracy classes are 1.2, indicating PT accuracy between 98.8 and 101.2%, 0.6, indicating PT accuracy between 99.4 and 100.6%, and 0.3, indicating PT accuracy between 99.7 and 100.3%. The next character in the label is a letter designating the burden rating. The typical burden designations and their corresponding ratings are as follows. The W rating indicates the PT will operate accurately as long as the burden doesn't exceed 12.5 volt amperes. The X rating indicates the PT will operate accurately as long as the burden doesn't exceed 25 volt amperes. The Y rating indicates the PT will operate accurately as long as the burden doesn't exceed 75 volt amperes. The Z rating indicates the PT will operate accurately as long as the burden doesn't exceed 200 volt amperes. And the double Z rating indicates the PT will operate accurately as long as the burden doesn't exceed 400 volt amperes. If at any time the burden exceeds the PT's rating, the accuracy classification will be compromised. In this example, the PT rated 0.6 double Z would have an accuracy between 99.4 and 100.6% as long as the burden of the PT remains under 400 volt amperes. Modern microprocessor-based protective relays support many different protective elements. These elements may require one or two power system quantities, such as current or voltage. If only one measured quantity is used, the protective element will respond to the measured quantity over time. If the protective element uses two quantities, such as both current and voltage, the element may respond to the phase angle between the two quantities, the magnitudes of the two quantities, or to a combination of magnitude and phase angle. In protective relaying, it is common to use an operating characteristic to show the relationship between the quantities that will cause the relay to operate. As stated earlier, if only one measured quantity is used, the protective element will respond to the measured quantity over time. The operating characteristic will take the form of a graph with the measured power system quantity plotted on the x-axis against time on the y-axis. The graph, or operating characteristic curve, clearly demarcates the boundaries between three regions. The first is the none-operate region, and as the name implies, the element will not operate when the intersection of the two measured quantities falls within this area. The second region is the operate region. The element will operate when the intersection of the two measured quantities falls within this area. The third region is the plotted curve representing the boundary between the operate and non-operate regions. If the measured quantity and time intersect on this curve, the element will operate. The pickup represents the minimum value of the measured quantity that will cause the element to operate. The x-axis is in multiples of the pickup. In feeder applications, a very common requirement is to remove a component if the amount of current flowing into the component exceeds certain levels over certain amounts of time. The time and instantaneous overcurrent elements provide this protective functionality. Let's take a closer look at their operation. Both elements require only current as the single measured system quantity, which is plotted on the x-axis. The x-axis is in multiples of pickup. As stated earlier, the y-axis is in units of time. The curve represents the boundary between the operate area, the area at and above the curve, and the non-operate area, the area below the curve and to the left of the pickup. The instantaneous overcurrent protective element operates once the current has exceeded a pre-programmed level. The device number for this function is 50. The relay will require some minimum or short time to operate. Where it is desired to have more time delay before the element operates for the purpose of coordinating with other protective relays, the time overcurrent protective element is used. The device number for this element is 51. The trip time varies inversely with current. Within a microprocessor-based relay, the element will typically support several characteristic curves. The three characteristic curves most commonly used in North America are called inverse, very inverse, and extremely inverse. They are said to be a family of curves. In other parts of the world, different sets of curves are used, and so the universal relay supports various sets or families of curves, in addition to allowing you to create your own curves. During the selection of the curve, the protection engineer will use what is termed a time multiplier to effectively shift the curve up or down on the time axis, while a scaling setting allows the normalization of the curve to a desired pickup level. That is to say that the x-axis will be multiples of pickup. It is very important to coordinate the overcurrent protection. Take the example system shown. If a fault were to appear, the fuse F1 should open. If it were to fail, the feeder circuit breaker should trip a short time later because its protection has been properly coordinated with the downstream fusing. Properly coordinated protective devices help to eliminate service interruptions due to temporary faults, minimize the extent of faults in order to reduce the number of customers affected, and locate the fault, thereby minimizing the service outages. Overcurrent protection within distribution feeders starts with a short circuit study from the source to the furthest endpoint of the system. Within a distribution system, overcurrent protection is commonly accomplished with fuses and relays. The coordination of the protective elements is done starting at the point furthest from the source and then moving back towards the source. When discussing feeder overcurrent element coordination, we must consider three situations: coordination between fuses and relays, and finally, coordination between relays. Let's take a look at each one. During the process of coordination, the operating characteristic curves of all overcurrent protective devices are plotted on a current versus time curve to ensure that no two curves cross and there is adequate discrimination between curves. The discrimination ensures that the device closest to the fault operates first, taking into account such things as timing errors, overshoot time, circuit breaker opening time, and safety margins. Operating characteristic curves are useful for determining the relay settings that will provide the necessary speed, selectivity, and sensitivity to protect the power system and to coordinate with other protective devices. The setting of a series of time overcurrent elements on a feeder or distribution circuit begins at the point farthest from the generating source. As the elements are set and coordinated back toward the generating sources, the time required to clear a fault becomes longer as the source is approached. Under certain fault conditions, this could be a disadvantage, and so instantaneous overcurrent elements are used in conjunction with the time overcurrent elements to provide high-speed primary protection. These elements must be set to pick up under maximum fault current conditions for three-phase faults somewhat short of the end of the line. The shaded area of the figure illustrates the improvement in tripping time obtained with instantaneous elements. In many areas of the distribution system, fusing is the most economical form of overcurrent protection, and so they are used in many locations in conjunction with protective relays. There are many different types of fuses. If the feeder is to supply a large load, the equipment manufacturer will make fuse recommendations. The basic characteristics of fuses are as follows. They consist of one or more silver wire or ribbon elements called fusible elements suspended in an envelope. When high currents flow, the fusible element melts almost instantaneously, disconnecting the protected element. The time current characteristics of a fuse have two curves, the pre-arcing curve and the total clearing time. The pre-arcing curve is the time between the initiation of a current large enough to cause the fusible element to melt and the instant when arcing occurs, while the total clearing time is the total time elapsing from the beginning of an overcurrent to the final circuit interruption. The time current characteristic curve of a fuse follows an I²T characteristic. That is to say, as the current goes up, the time drops by the square of the current increase. When selecting a fuse, the criteria that is taken into consideration is as follows: the melting curves, the load carrying capabilities, the continuous current, which is defined as the maximum current expected for 3 hours without damage to the fuse, the fuse's hot load pickup, which is the maximum current that is carried continuously, then interrupted and immediately reapplied, which does not blow the fuse, cold load pickup, voltage rating, and interrupting rating. The variables involved in fuse selection for a specific application vary significantly with the type of load and will not be covered further. We will focus only on the final fuse curve. The operating time of a fuse is a function of the pre-arcing or melting and arcing time, and follows the I²T law as stated earlier. For proper coordination, total I²T of the secondary fuse shouldn't exceed the pre-arcing of the primary fuse. This is established if the current ratio of the primary versus the secondary fuse current rating is 2 or greater for fuses of the same type. It is important to note that the relay should back the fuse up over full current range, and that no characteristic crossing occurs. The relay characteristic curve best suited for coordination with fuses is the extremely inverse, which is similar to the I²T fuse curves. For extremely inverse relay curves, the primary pickup current setting should be 3 times fuse rating. For other relay curves, up to 4 times fuse rating should be considered, therefore ensuring that there is no crossover between the relay and the fuse curve. To account for CT saturation and errors, electromechanical relay overshoot, timing errors, and fuse errors, a minimum discrimination time of 0.4 seconds should be used. The following table is a list of recommended discrimination times between relay technologies to ensure proper coordination. In some applications, it is desirable to add directionality to the overcurrent element. What we mean by directionality is that the overcurrent element or elements are disabled by a signal from an element that looks at the direction of power flow. This type of element is referred to as a directional element. Once the directional element determines that the phase angle between the current and voltage is such that power is flowing in the tripping direction, the directional element removes the disable from the overcurrent element, allowing the overcurrent element to function. A simple example of an application of the directional element can be found at our example industrial customer site. This customer supplements his power requirements with on-site generation. If the utility power were to fail, the feeder connecting the customer to the utility must trip to ensure that the power generated by the customer doesn't feed back onto the incoming line. The overcurrent element would have a high set pickup for power flowing from the utility into the user, and a low set pickup if the power is flowing from the user back to the utility. If lightning strikes the conductors of an overhead feeder, or a strong wind causes 2 phases of the feeder to touch, an arc will be formed. The arc ionizes the air and turns it into a conductor. The arc is then maintained by the power being supplied to the feeder. This is an example of a common source of an intermittent overhead feeder fault. This type of fault is cleared with auto-reclosure. Once the fault has occurred, the auto-recloser protective element generates a signal to remove power from the feeder for a period of time long enough to allow the ionized air to dissipate, and then generates a signal to reapply power to restore service.